Divulge into talking about complex carbohydrates, there's just two things that I really wanted to mention would be that of oligosaccharides. If you remember when we talked about like oligo meaning just a few, like 15 or so maybe, these are formed by enzymes known as glycosyltransferases. These are going to be the enzymes that are involved in catalyzing the glycosidic bonds. You know, it's enzyme because it's in the ases, and they are going to catalyze the formation of glycosidic bonds. Okay, so that's it for the oligosaccharides. Now, so we talked about disaccharides already. Let's talk about polysaccharides, and those are going to get a lot of attention. So there's known as homopolymers, and then there's other types known as heteropolymers. But we really didn't talk too much about heteropolymers, so most of these are going to be homopolymers, as you can imagine from the name itself what it implies. But I'm going to mention glycogen, amylose, amylopectin, and cellulose. This shouldn't be too complicated if you remember, because we kind of already talked about the individual subunits of these, and understanding the individual structures of the subunits tells us a lot about what the polymers are going to look like. So glycogen, as its name implies, is a sugar-based compound, gly, but its function is primarily for storage. Storage of sugar in animals. What are the two things that give it the ability to do this? Well, the two bonds that it consists of would be an alpha 1 to 4 glycosidic linkage. That's kind of the straightforward part of it. But if it was just that, it wouldn't be very stable. And glycogen is kind of an energy supply for the last second. And so what gives us this is that it has these alpha 1 to 6 branched linkages. And so the branched linkages, I guess like kind of a misconception time here, and I just really want to drive home the point that with glycogen it is highly branched. It is the most branched molecule out of all of these. Okay, so with this, it's not that, so say you had a long series of polymers just running in tandem like this, and how could you compact them and form them into the storage? This highly branched structure, if we were to really think about this maximizes my surface area for storage, right? So say that we had, just to say, compare these two boxes here. You have a long series of alpha glucose polymers, and you're just going to throw them in here all crazy like this. Whoop-de-doo, right? They're not going to be able to store as well, as opposed to things that I had that were literally in the forms of this. And this is not driving home the actual structures of that of glycogen so much as the point that I'm just saying that it has that maximized surface area, and if you maximize your surface area, you can compact a lot of energy and a lot of fuel, a lot of, in this case, sugar, into a very small amount of space. Hopefully that's what I'm trying to drive home, and hopefully I've succeeded in doing that. So for amylose, this is something really kind of unique to plants. This is what makes, if you've ever had pasta or any other type of starch on the planet, it's colloquially referred to as starch. This is just alpha 1 to 4 linkages. Not really much that I can say more about amylose. However, his closely related friend here, amylopectin, is analogous. I don't think it's homologous, but it's analogous to glycogen, but it's like the glycogen of plants. So yes, it has the alpha 1,4, but it also has the alpha 1,6 linkage there. But this is less branched than what we had from this. So the reason why this would be less branched than, say, that of glycogen is because, as you might imagine, I probably could have just written that out or stated it instead of writing it. Plants don't run marathons. Plants don't run at all. They don't get up and move. They don't have nearly as high of an energy supply as we do. Okay, so plants, on the whole, do not use up as much ATP as we do, which is why they can regrow their limbs. They do not have to pay the price of metabolism and, by extension, oxidation as much as we do. They live longer than we do. Why? Because they don't get up and run. because there's less oxidation going on inside of them. Anyways, so for cellulose, let's just talk about this. So cellulose, whereas all these guys were all alpha glucose or alpha sugar polymers, cellulose, on the other hand, is not. Cellulose is beta 1,4 chains linking it together. Cellulose is not branched, but what we do is these beta structures here can have hydrogen bonding between the fibers, is what I like to call them. So let's just say that we have, you have a beta chain here, literally a long series of beta glucoses connecting each other. Well, in between those, we're going to have hydrogen bonding connecting those two there, and it's going to make it very, very, very strong by doing that. This is what makes wood, for the most part at least. This term here, fiber, is literally where we get the term dietary fiber, like for old people and for young people who should be taking their fiber. This really does exist in two forms, but I guess the point that I was making is that this is a beta linkage. It's from beta glucose bonds coming together. It's very, very stable. It's very difficult to break.